Another key question that is often confusing to many who use logistic regression is how to interpret the regression function. After all, in linear regression, the regression function clearly shows the relationships between the predictor variables and the target variable. Can logistic regression functions be interpreted in the same way? Well, the answer to this question is yes and no. Yes, we can describe the relationships between the predictors and the target variable using the coefficients of the function. But no, we cannot do it in the same way as in linear regression. Let me demonstrate this using an example. Suppose that a bank is trying to build a logistic regression model that can be used to predict whether a customer is likely to respond to a personal loan offer or not. Using the dataset, the computer software produces the following result. The table here includes 5 columns. The first column lists the 12 predictor variables and the constant value. The predictor variables include a mixture of numeric variables such as customer age, years of work experience, and income, and categorical variables such as whether the customer has a CD account and whether the customer banks online, and etc. The second column contains the coefficients, which can be used to build the regression model. Based on these coefficients, the regression model looks like this. The logit equals to the constant negative 13.201 minus 0.045 times age plus 0.057 times experience plus 0.066 times income, and etc. Well, in linear regression, the coefficients show the impact on the value of the target variable with 1 unit change in the predictor variable, holding all the other predictor variables constant. Can we interpret the coefficients here in the same way? Well, the answer is yes, but the impact is on the logit, not on the probability. For example, if the customer's age increases by 1 unit, which is 1 year, the logit value will decrease by 0.045. However, it is very difficult for a layperson who does not understand logistic regression to understand what you meant by that. How can we make the interpretation of the coefficients a little easier to understand? Well, it will be very difficult to interpret the impact of x on y using the probability, because the changes in probability caused by 1 unit change in x are likely to be different depending on the value of x. However, we have a solution to this problem. Instead of interpreting in terms of probability, we can do it in terms of odds, which is essentially the same thing as probability. Let's look at how we can do that in the next slide. Well, let's look at another simple example. In this case, we only have one predictor variable, gender, in the logistic regression function. And gender is a categorical variable. If the person is female, then gender equals 1. For someone who is not female, the gender equals to 0. Since there are only 2 possibilities for the gender variable, the logit of this function can only have one of the 2 values. If gender equal to 0, then the logit equals to negative 0.7567. And if gender is 1, the logit will equal to negative 0.7567 plus 1 times 0.4373. So, if we convert them into odds, the odds of someone who is not female the odds value is e raised to the power of negative 0.7567. And for someone who is female, the odds value is e raised to the power of negative 0.7567 plus 0.4373, right? Okay, now let's look at something called odds ratio, which is the ratio between the two odds that we just computed. Right. So if you look at this, the ratio of the odds value we just computed would be e raised to the power of negative 0.7567 plus 0.4373 divided by e raised to the power of negative 0.7567. And if you do the calculation, it will show you that the result is actually e raised to the power of 0.4373 or 1.55. Well, you probably have noticed a couple things from here. First, the difference between the predicted values of the two equations is 1. Because for female, the value is 1, and for male, the predicted value is 0. And second, the odds ratio happens to be e raised to the power of the coefficient of the predicted variable, which is gender. And in this case, it's e raised to the power of 0.4373. So this gives us an idea about how to interpret the coefficients. It seems that the odds ratio would remain the same for every 1 unit change in the predict variable. So in this example, since the odds ratio is 1.55, we can state that females who have the gender value of 1 would have 1.55 times the odds of having the outcome compared to males who have the gender value of 0. So recall that odds and the probability move in the same direction. So a higher odds also means a higher probability. So in other words, females would have a higher probability of having the outcome compared to males. The example you just saw only has a categorical variable with the possible values of 1 or 0. Can this interpretation be extended to numeric variables? The answer is yes. So we can generalize our findings here to if we increase x1 by 1 unit of measure, holding x2, x3, and the rest of the x's constant, then e raised to the power of beta 1 which is the coefficient of x1 in the logistic regression function, is the factor by which the odds of belonging to the target class increases. And e raised to the power of beta 1 is called the odds ratio. Of course, odds or probability values do not always increase when the value of x increases by 1 unit. There are situations where the odds or probability decrease when the value of x increases by 1 unit, suggesting a negative relationship. So when the odds ratio is less than 1, then it means that the odds actually decreases when the value of x increases. We will look at an example in the next slide. Now let's revisit the personal loan example. How do we interpret the coefficient value for income, which is 0.066 in the logistic regression model here? Well, as we discussed in the previous slide, the odds ratio for income would be e raised to the power of 0.066, and we can find that value by using the exponential function in Excel, and that value equals to 1.0682. This means that holding all other predictor variables constant, increasing income by 1 unit, which is $1,000 in this particular case, increases the odds of the customer responding to the loan offer by a factor of 1.0682. And this suggests that income and odds or probability have a positive relationship. That is, if the income increases, the odds or probability of responding also increases. As 1.0682 is odds ratio, one simpler way to understand the magnitude of the impact is to subtract 1 from the odds ratio and multiply by 100%. For example, 1.0682 minus 1 and multiply that by 100%. And this would give you 6.82%, which means that 1 unit increase in income would result in 6.82% increase in odds of responding. However, keep in mind that this does not translate to 6.82% increase in probability, as odds and probability are not proportional to each other. So what about the coefficient for the age variable, which is negative 0.045? The odds ratio can be computed as e raised to the power of negative 0.045. And if you compute it in Excel, you will get 0.9560. As you can see here, if age increases by 1 unit, the odds value actually decreases because the odds ratio is less than 1. If you subtract 1 from this number, and multiply it by 100%, you will get negative 4.4%. And this means that holding all other predictor variables constant, increasing age by 1 unit would result in 4.4% reduction in the odds of the customer responding to the loan offer. As you can see from this example, when the odds ratio is less than 1, the relationship between the variable and the target is negative. Let's summarize the properties of odds ratio. First, odds ratio is how we can use the coefficients to show the magnitude and the direction of the association between the predictor variables and the odds of the case belonging to the success class. If the odds ratio happens to be 1, this would only happen when the coefficient value is 0, because e raised to the power of 0 is 1. This suggests that the predictor variable has no impact or no association with the odds. That makes sense because if the coefficient is 0, then the predictor variable would not even appear in the regression model. If the odds ratio is greater than 1, then the predictor and odds or probability of the case belonging to the success class would have a positive relationship. That is, if the value of the predictor variable increases, the odds or probability of belonging to the success class also increases. If the odds ratio is less than 1, then the predictor and the odds or probability of the case belonging to the success class would have a negative relationship. That is, if the value of the predictor variable increases, the odds or probability of belonging to the success class decreases. The diagram in this slide illustrates these key points related to odds ratio. Now that you understand how logistic regression works and how to interpret its results and the model function, let's conclude this lecture with a couple of additional issues to keep in mind when using logistic regression. Like a linear regression, one needs to be aware of the problem of multicollinearity when using logistic regression. Multicollinearity happens if one predictor is a linear combination of other predictor or predictors. The solution to this problem is to inspect the predictor variables prior to performing logistic regression and remove variables that are highly correlated. Another technique is to use principal component analysis or PCA to remove any redundancy in the data. The other issue to keep in mind is that overly complex models have the danger of overfitting, and as a result, the model will generate large prediction errors when being applied to a new dataset. In regression techniques, one may not start with many predictor variables, but when you include derived variables such as dummy variables, interaction terms, and the polynomial terms, you may end up with many variables. On one hand, these derived variables can increase model flexibility and help capture complex relationships in the data. But on the other hand, it also creates complexity and may lead to overfitting. One solution to this problem is to use the automatic variable selection process to reduce the complexity of the model. Popular techniques such as forward selection, backward elimination, stepwise reduction, or best subsets can be applied to achieve that.